Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll discuss abstract sketch of the machine learning process. Training data is the most important aspect of machine learning algorithm. We have already studied that without training data, it is next to impossible for us to train a machine learning model. We have said that no data, no machine learning, and I hope you remember that mantra very well. Okay, so training data comes in the form of features and labels, right? Remember, labels may be present or not present depending on the type of the machine learning problem. In case of supervised learning algorithm, we'll have labels present with each and every training example, whereas in case of unsupervised learning problem, labels will not be present. The training data is represented by a boldface letter D. So we will be following this convention throughout this course. We will represent training data with boldface D, and each example has a feature vector associated with it. By feature vector, what we mean is there are M features associated with every example, and those M features form a feature vector for that example. Okay, and since X is a feature, we again represent it with a boldface. So all the boldface letters, they represent some kind of a vector notation, right? So they are not scalar, they are vectors, right? And ith example is represented by X superscript I. This is not the power of X, but this is ith example or ith training example, and is a feature vector associated with the ith training example. The label is denoted by Y, and since label is a scalar quantity, it will be not boldface, but Y, the boldface Y is used to represent list of label for all the examples. Okay, and if we have a multi-label problem, we use capital Y, again boldface, to represent the label vector for all the examples. Got it? So for single label problem, the boldface Y represent labels for all the examples. In case of multi-label problem, the capital Y, again boldface, is used to represent the label vector for all the examples. Now we have D, which is the training data. It is set of n training examples, and it's a set of ordered pairs containing features and labels. So we can compactly represent D as ordered pair between features and labels, right? So this is ith example, this is the feature vector corresponding to ith example, and is a label corresponding to ith example. This X should have been actually boldface because this is a feature vector. So we'll rectify it and upload a new slide. In the same manner, this X should also be a boldface X because this is again a feature vector corresponding to ith example. So what we will follow in this course is, generally in order to get efficient implementation of the algorithms, we will be using vectorization. Okay, we will study what vectorization is in the course, but in the vectorized implementation, what happens is we represent the feature matrix X as a transpose of individual feature vector. So we have n examples, so n is used to represent examples. So this is a feature vector corresponding to first example, this is a feature vector corresponding to the second example, and this is feature vector corresponding to nth example. And remember, vector, we use a column notation, right? A vector by default will be a column vector. So what we do here is we represent, so we take a transpose of individual feature vector. So what we get is we get a feature vector in a row, right? So every row contains feature vector for that particular example, right? So we have n such kind of a feature vector. So we will have n cross m matrix, which is a feature matrix, n being the number of examples, training examples, and m is number of features for each example. Okay, and again the labels are represented either as a label vector or a label matrix. The entire training data is divided into three subsets or three partitions, to be specific. One is training set, second is a validation set, and third is a testing set. So we use 60% data typically for training, 20% for validation, and 20% for test. And the training data is represented by D sub train, validation data is represented by D sub val, and the test data is represented by D sub test. And each of these data has the feature matrix and the label vector associated with it. Okay, again these percentages are only for the purpose of demonstration, and you are free to change these percentages depending on the availability of data. Training set is used for training the model. Validation data is used for tuning any hyperparameters. Example is regularization rate, which we will study in the linear regression, where we want to control the complexity of the model by using some penalty, and that penalty is controlled by regularization rate, and this is the hyperparameter. So hyperparameters are some kind of a tunable parameters or the settings that are provided by the designer of the model. Okay, and these hyperparameters are generally not optimized like other parameters, but we need to do a specialized model selection for hyperparameter search. So validation data is used for tuning the hyperparameters. And remember, we never use test data for training or validation, but it is only used for evaluation of the model. And test data is never exposed to the training process. It is kept aside as if we do not know about its existence. Okay, and the main purpose of the test data is that we cannot simulate future, so we need to have some representation of what kind of data we are likely to see in the future, and test data provides us that particular set. Okay, and again remember why machine learning works from our second video. So we said that machine learning works because it makes an assumption that training data and test data comes from the same distribution. Okay, and that's why whenever we set aside some data from the training set as test data, it provides a reasonable representation of the kind of data that we are going to see in the future. Instead of just fixing set of examples for training and validation, what we do is we essentially use different sets for training and validation. So this provides a robust way of estimating how the model is performing, right? Because what might happen is that because we have fixed the training set, it could just by chance will get us a good result on that set, but that may not be that representative of a general situation. So in cross validation, what we do is we use different training and validation set, and we train the model multiple times, and we will see how to use this cross validation after a few slides. So this is how we do the cross validation. So we partition the training set into k equal partitions. We use k-1 partitions for training and the remaining one for validation, right? So one of the extreme form of this is n-1 fold cross validation. Remember, n is the total number of training examples. So what we do is we actually put each example into a separate partition. Thus we create n partitions for n training examples. Okay, and at a time we use, just like k-1 partition, we use n-1 examples for training and the remaining example for validation. Okay, so this is called as leave one out cross validation. This is called as k-fold cross validation, and this is called as leave one out cross validation, where we have cross validation where each partition has exactly one example. Okay, now you can imagine whenever we have a k-fold cross validation, we will train model k times, right? And hence we need to evaluate the model also k times. So at every time, every of this k time, we will have a different training set and different validation set. So we will get k different training metrics and k different validation metrics. And what we do is we select best of these methods and report their metric on the test set. So what we do is we average across k runs and we select best of this model. So we essentially get k different models, right? Because we are training the model k different times, so we get k different models. So we can select the best out of these K models, right? And how do we select which one is the best? We look at the performance from the validation set, and whichever one has the best performance, we essentially select that model as our candidate model, okay? And we then use it to test the performance on the test set and report the metric numbers on that particular model. So this is what happens in cross validation in a pictorial form. So this is our entire training data, and we had two sets like training data and test data, right? So we typically use 80% data for training and 20% data for test, but you can change these percentages depending on amount of data that is available to you. Some people also do 70-30 and so on, right? And now remember, here there is no validation data that is set aside separately. Instead of that, what we do is we partition this particular training data into 5 different folds or 5 different partitions, right? Partition is the between 2 folds there are no examples common, right? So that is what is called as partition. And if we union all these folds, this will equal to the original training data. So that is the definition of the partition, okay? And what we do is in the first run we use, let's say, fold 1 for validation, and we use remaining 4 folds for training. In the second run we use fold 2 as a validation and remaining folds for training, and so on. So this is how we will have 5 different runs, right? 5 different models. One that is trained on this particular set, the second one trained on the second split, the third one trained on the third split, and so on, right? And then we'll select the one which has got the best accuracy on the validation set, and we essentially do final evaluation on that model using the test set and report the metric numbers. So each example in the training set is represented by m different features, and some of these features could be real valued feature and some of the features could be discrete valued features. And the real valued features may be on different scales, and if they are on different scale, that is not really good for training of the model. So what we need to do is we need to take these real valued features and we need to normalize them so that all of them are on the same scale. This leads to faster conversion. And then there could be discrete attributes or discrete features. We need to convert them into numbers using one of the following scheme, either using one-hot encoding, using hashing, or embedding. We'll study each of these techniques in using a collab in the practice course. To examine the relationship between features and labels, we typically use data visualization techniques. We use histograms, pair plots to check if features are correlated to labels. So this helps us to know whether feature have some information to predict the outcome of label. If features do not have any information, then we probably do not have any hope of learning to predict the label. So if effective features are not present, a useful model cannot be learned. In addition to that, we can perform statistical test like chi-square test in order to get the relationship between features and labels. The next problem that could happen is that there may be certain features that are missing from some examples, and this could happen because of, let's say, some kind of errors in the data capture process or faulty measurement equipment, or because of variety of reasons. So if data set has missing values, we need to either remove examples containing the missing values, but what happens in the process is that some examples are lost, and if we do not have large number of training data points, then we cannot afford to lose some of the examples. A better strategy is to fill the missing values using some kind of, let's say, we can use different strategies to fill the missing values, right? So we can either use the average value of the feature to fill in the missing value, or we can take some other statistics and use that to fill the missing value. So there are some standard tricks to fill up the missing values, and we'll also study them in the practice course. Finally, there is a class imbalance problem, which is a commonplace in real world scenarios. So what happens in class imbalance is there are too many training examples from one class and too few examples from the other class. And I'm actually giving you an example from a supervised learning setting and specifically from classification setting. We have a situation where because of abundance of the data we might have too many examples from one class and very little examples from the other class. When this happens, typically the classification algorithm tends to predict all the examples into the majority class, right? Majority class is the one which has got too many training examples, and the minority class is not getting learned correctly, and which is not a desirable situation. So in such situation, one simple solution could be oversampling examples from minority class. We can repeatedly sample examples and add those examples, so which is very similar to either copying the examples again or sampling it based on certain distribution. And then what happens is that we somehow make the training set balanced in terms of examples from different classes, and then that might help us in addressing the class imbalance problem. There are more sophisticated techniques that are also proposed in the literature for handling class imbalance, and in my opinion, this is a very, very important technique that you should understand for doing effective machine learning, because class imbalance is something that you will often encounter in the practice, and you need to have skills to address class imbalance problems. So that was all about training data. So we essentially talked about training data, features and labels, and then there are various issues that we can encounter with training data. So those issues could be features not being on the same scale, then missing data, or even class imbalance, the problem that we observe with a label distribution, right? So we discussed what are different strategies to handle each of these issues, and we will have a practical demonstration of all these techniques in the machine learning practice course. So second component of the machine learning process is model, right? So once you have training data where you have features and labels, we need to essentially fix a model that provides a mathematical relationship or mathematical function between features and the label. So we have a training set in terms of feature matrix X and a label vector Y for a single label case and a label matrix for multi-label problems. So we use H sub W to represent the model, where W is a weight vector of the model, and H provides the mapping between the feature vector and the output label. Let's talk about loss function. Loss function measures the difference between the actual and the predicted label. We have talked about it in a couple of videos in the past. The loss function is represented by a letter J, and loss function is a function of weight vectors. So essentially what happens is the loss depends on the predicted label, and predicted label in turn depends on the weights that are used to parameterize the model, and hence the loss function is a function of the weight vector. Every time the weight vector is changed, we get a new instance of the model, which leads to different predictions and hence causes a change in the loss value. The loss function can be convex or non-convex depending on the model function class. Linear and logistic regression support vector machines have a convex loss function, while the loss functions for neural networks are non-convex in nature. The convex loss functions are easier to optimize than the non-convex ones.